Let's take a look at an example of an estimate that we take out of our sampling that it derives more of a functional picture than simply a statistical view of estimating our baseline. When we learned about statistical process control, one of the charts we learned about is the P-chart, a measure of the predictability or the level of control of the number of defectives that a process creates as it goes on. Here's a quick P-chart of an example process step where the defective range is expected to fall in the 0 to 9% range, the lower and upper control limits, with an established estimated value of just over 4%. So to get to this level in a control chart, you had to be able to estimate from samples of data and their deviations what the sigma, or the standard deviation of the population, would be. So these lines are plus and minus 3 sigma from the anticipated process mean in this chart. So that's one form of estimation. That kind of estimation already had to have gone on in order to draw this chart. But we want to see other things we can do functionally with those kinds of estimates as we move forward. Here's another step, step B, where the estimate rate for defectives is just over 5% there at the midline, and the acceptable range, the plus or minus 3 sigma on that, has been estimated to be not quite 3% or 2.8%, up to almost 8%, 7.7%. So the control limits of a control chart give us a range within which we can expect the value to fall, with the midline giving us the estimated value. So that plus or minus 3 sigma is based on an estimate, a point estimate of the population sigma based on all the sampling that has gone on. So that's not what I'm talking about right now, but that kind of point estimation had to have occurred every time we draw a control chart using statistical process control. The question becomes, what else can I estimate when I put these kinds of things together? Suppose I want to connect those two processes in series as I go. So I've included the control limits from the chart here, so that I have those, but I want to measure the reliability of a process, not its defective rate. So 1 minus the defective rate gives me the reliability. So I can take 1 minus each of those 6 numbers there to the left, and I can come up with the reliability. Notice that 1 minus the upper control limit gives me my worst case scenario for reliability, because the larger my number of defects, the less my reliability is. So it's kind of a swapping. The upper control limit becomes the worst case, the lower control limit becomes the best case. So these estimates are simply 1 minus the value obtained from the limits on the control chart. And I do that for each of the 2 steps. When I connect those processes together in series, I have to take the product of those numbers as I look at them to see what the reliability of the chances of getting through step 1 and step 2 without an error would be. So I end up with a new form of estimate that isn't simply the point estimate based on the sigma of the underlying sample, but now I have 3 point estimates for the reliability of the process. Note this is 3 different estimates at this point. What is my worst expected reliability? This combined process is expected to have a reliability as low as 84%. The actual expected reliability based on the expected values from the original functions is just over 90%. And the anticipated best case reliability would be 97.2%. So I have 3 different estimates for reliability. If I'm trying to be an optimist and act like my process is going to do very, very well, I might use the 97.2. If I'm trying to be a realist and warn management of what could happen, it could be this process will perform as low as 84%. So if I tell my management only the 90.8% point estimate and they plan accordingly, standard variation in statistics tells us that half the time our data will fall below that mean. I want to be careful how I use that data. I could repeat that same calculation, take the same control limit data, the same reliability-based data, but do a calculation for parallel processes. Remember, with parallel processes reliability, 2 steps in parallel have a higher reliability than either of their components. So here I'm using a different formula. I'm actually taking the probability that both will, 1 minus the probability that both will fail as I go through. So again, my worst case performance in parallel is 99% reliability. My best case is a reliability of 1. But again, I've got 3 different point estimates as I go through. I could do the same calculation for my backup process, put steps 1 out in place with step 2 as a backup to that process, and I end up with a reliability based on the different reliability formula of the reliability of the first step plus the reliability of the second step times the reliability of the first step failing. That's your reliability failing. Okay. So all three of these ways of looking at reliability data come up with new point estimates. They're estimates of our values based on samples that have been drawn. That's what a point estimate is. It's estimating something about the population from data in our sample. And in statistical process control, all of our data is sample data drawn from the process. The control chart had to be able to estimate a sigma from the sample in order to draw the control limits. But once we've done that, we use that data functionally to create other kinds of point estimates that are useful to management, but that ultimately the reliability of these measures is based on those original samples. So if we built good control charts and ran a sound practice of statistical process control, these estimates will be highly usable and highly reliable in a management setting.